Okay, so we're doing a countdown of the last topics in the class. Uh, and these are all related to friction. It's the first thing in the class that's kind of semi not connected to the flow of everything we've done so far. But we're starting out with square threaded screws. And then belt friction. And then bearing friction. And there's two kinds of bearing friction. Well, we'll get to that when we get to it. But we're almost done with square threaded screws. You know, so square threaded screws. I talked about the connection between this and sliding a mass up an incline. So this is the problem that you're dealing with. This theta, the angle of the ramp is the angle of the thread. W is the weight that's supported. And Q is the force that is either, if it's going the direction shown here, you'd be pushing this thing up the, lifting the weight along the thread, or if Q is negative, it would be moving the thing down, the weight down the screw. But we still have to relate the angle of the thread and let's see, the angle of the thread and that force Q to something that's meaningful to the problem. So first we want to replace this theta with parameters that describe the screw. Okay, so if you have a screw like this, and these are the threads. The pitch is the distance between the two adjacent threads looking at the same point. Okay. But what we really want is the lead. And the lead is, so if an ant is walking up the thread, it doesn't have to be an ant, it just has to be small. how much higher is he? It could be a female ant. The next time he gets to that same point on the screw. Okay, so try this again. So here are the threads. Okay, and so like if this ant is going around, I'm not really a great ant drawing mind, but okay, so he's going around this way. The next time he comes around, he's there, and so this is the lead. Okay, so how is that different from the pitch? You may be asking yourselves. Or you might just be writing notes and spacing out and thinking about something else. But the difference is sometimes some kinds of threads, the ant would not get from there to there. So the lead is different from the pitch. For double threads. And in a double thread, the ant would be here. And go around. And the next time you saw him in this spot, he would be here. Okay. So in this case, this would be the lead. And this would be the pitch, and they'd be different. Okay, so what we want is the lead. If it's a single thread, they're the same thing, but if it's a double thread, we want the lead, not the pitch. If the screw has a radius r, okay, then that angle, so you can think of taking one revolution of this thread and straightening it out, okay? Then what you have is a triangle where this is the lead and the horizontal leg is the circumference, so that would be 2 pi r. Okay, and then that angle theta would be the inverse tangent of let's give this lead a name, L, lowercase l. So theta would be the inverse tangent of L over 2 pi r. Okay, so like I said, screws aren't like, if they were described by angles, then we wouldn't have to worry about this, but they're not, so we have to convert from the lead to the angle. And then the other thing we have to do is that force Q so we want to calculate the couple M required for motion. Rather than the force Q. I mentioned before that force Q that's required to push the screw up the external thread would be like a force that you actually were applying to the outer edge of the thread. It's not a physical thing at all. And so you just have to keep in mind, notice that this couple that's required to turn it is equal to times R. And so that Q is equal to M over R. So you can first do the calculation with the angle and with Q, and then substitute in whenever you want. But eventually you're going to need to get this problem in terms of the couple and the lead. Okay, let's do an example problem. So let's say we have a square threaded screw. Let me give a radius. So with a radius of 1 centimeter, 0.01 meters. And a lead of 0.004 meters, so 4 millimeters. And let's say that there's a coefficient of static friction of 0.1. If the screw supports a weight of 2,000 newtons, then first, part A, what's the couple required to initiate motion up? And then second, same question, but down. Okay, well, first let's get that angle. We have a lead of 4 millimeters. And the radius was 1 centimeter. So this circumference is 2 times pi times 0.001. So the angle theta for the ramp is the inverse tangent of 0.004 divided by that's 0.0628. Can someone calculate that? What? Yeah, please. 3.64 degrees. Okay. I think that sounds about right. Okay, so now let's go through, we'll do this calculation, we'll calculate that Q and then just get the couple from that at the end. This is obviously not drawn to scale, that's a pretty tiny angle, but 3.64 degrees and we're looking for this force Q. There's a downward force of 2,000. And so a free body diagram So the first calculation we're doing is starting motion up the ramp. Friction is going to resist that, so friction is going this way with a magnitude of 0.1 N. Our rotation matrix is cosine of 3.64, sine of 3.64, 0, negative sine of 3.64, cosine 3.64, 0, and then 0, 0, 1. First, I'll multiply that by the vector 0, negative 2,000, 0. And you get negative 126.98, negative 1995.97, and then 0. And then we'll multiply that rotation matrix times the force up the ramp, which is W, 0, 0. And you get 0.998 W, negative 0.063 W, 0. And so Newton's second law says negative 126.98, negative 1995.97. That's the weight force in the new coordinate system. You know, I'm just as a reminder, all I'm doing is representing all these force vectors in this coordinate system. Yes, thank you. Okay, so this first vector is just the weight force. Now we're adding that Q vector, so 0.998 Q, negative 0.063 Q. And now the normal force and the friction force. The normal force is in the positive Y direction. The friction force is in the negative X direction. So we have plus negative 0.1 N, and then N for the Y. And that's everything. That's equal to zeros. And so we have two equations. The first one says 0.998 Q minus 0.1 N is equal to 126.98. The second one says negative 0.063 Q plus N is equal to positive 1995.97. And you get Q is equal to 329.31. N is equal to 2016.72. And now finally, the couple that's required is equal to Q times R. R is 0.01 meters, so this couple is 3.29 Newton meters. And that means, like, so how would you apply that couple? Like if the screw had, you know, if you were turning this screw by applying a couple like this, and you're applying a force here and a force here, and the distance between these two, some big R, then this would be equal to F times R. Any questions about that? There's not really too much I can do to make these problems any different than that. That's just what the problems look like. I could maybe solve for different variables, but I probably won't. So now we're just going to do the same thing to calculate what couple is required to initiate motion down. Is that couple going to be bigger or smaller than the one we just calculated? Smaller, yep, because gravity is helping instead of hurting. Okay, so for part B, so now the free body diagram looks like this. We have the downward force of 2,000. We have the Q going the other direction. We have the normal force, and then the friction force. Remember, it's opposing the motion, so friction force is going to be opposite in this case. So 0.1 N going that way. So multiply the rotation matrix by the 0, -2,000, 0. You get the same thing we did before. So -126.98, -1995. 0.97, thanks. And now multiply that matrix by, this time the Q is in the opposite direction. So I'll write it as -Q 0, 0. And you just get all the components switched. So -0.998, +0.063. And then Newton's second law says -126.98, -1995.97, plus -0.998 Q, +0.063 Q. And then the friction force this time is +0.1 N in the X direction, and the normal force is N in the positive Y direction. And those are equal to zeros. So our system of equations says 0.998 Q plus 0.1 N is equal to 126.98. And the second equation says +0.063 Q plus N is equal to +1995.97. And you get that Q is equal to 72.31. And the normal force, which we don't care about, is 1991.41. The Q we got in the first case was bigger. It was, 329 before, now it's 72. And the couple then is equal to Q times R, which is 0.72 Newton meters.
So if that number were like negative, would that mean that this thing would be moving?
That's right. Yep. That just means that, yeah, you don't want a jack that just drops down if you take the force away. So that is not a well-designed square-threaded screw, or problem anyways. But yeah, that would just mean that you had to hold it in place, or else it would just drift back down. Any other questions about this?
Don't take the rotation matrix of the friction is already in the right.
That's right. That's exactly right. So if you look at this free body diagram, you can see that there are two forces, the weight and Q are vertical and horizontal, but then the normal force and the friction are lined up with the coordinate axes, the rotated coordinate axes. So you don't have to mess with those. Those are already in place. Any other questions?
Is there any reason to rotate Q and 1000?
No, there's not. Yeah, I don't think, I think it's just always those four forces. I can't think of any other forces coming up. So yeah, if you could do the same thing and just leave it in a non-rotated coordinate system. And then you'd have to use the rotation matrix for the friction and the normal force. But when you solve the problem, you'd get the same stuff for the variables. I think you should do that. If you ever did that in like an engineering class, it would like blow their mind, I'll bet. Like, what are you doing? Okay, so that's it for square threaded screws. And now we're going into belt friction. Okay, so now we're done with, square threaded screws. Belt friction and bearings. And we are now done with square threaded screws, going on to belt friction. This is the one that I'm not going to make you derive because it goes through like differential equations and stuff. And so I'm just going to give you this and you'll just have to trust it. But the idea of belt friction is this. Ooh, this is such a good drawing. I wonder if I can do that again. Okay, so imagine Rapunzel in her tower. There's the one window, and this like prince is trying to climb up, So here's Rapunzel. He's like, let down your hair, so she does. And then he grabs onto the hair. And this is how much he enjoys that. You know, that does not look comfortable at all. But now, oh, okay, this is important. There's a pole outside her window. Okay. I didn't tell you that before, but it's important. Okay, so now imagine this. Here's the window. Here's the pole. But this time Rapunzel's smart. She takes her hair over to here and wraps it around this pole a bunch of times. And then from the pole it goes down and this jerk grabs it. And this is how much more pleasant it is. Okay? So what she knows about is belt friction, because the friction of her hair wrapping around that bearing of some kind takes up can take up the vast majority of the force that would be required just straight if that friction wasn't being taken advantage of. So belt friction reduces the force required at one end of a cable to support a given force. In this example, the given force is the weight of the prince or whatever this guy is. It's probably a prince. He looks pretty handsome. He's got nice hair. So here's how you do this calculation. So if this is, this is like a cross section of the bearing. And you have a cable that's in contact with some part of this bearing. This T2 is the given higher force. That's the prince's weight. Oh man, I should have made this guy. This is what I'm doing next year. I'm making this guy Prince. Come on, Apollonia. Let's go to Lake Minnetonka. That was Prince's voice. Okay, so notice that there's some angle that's in contact with the cable. Okay, so this angle is, we'll call it beta. This T1 is the force required to support T2. You want that to be as small as possible. And the equation that relates these two things is T2 over T1 is equal to E to the power of coefficient of friction times that angle beta. And notice beta can be greater than 2 pi if the thing wraps around and around and around. So you have to take all that into account. You know, you could have, if it wraps around 3 times, beta could be 6 pi. And make a note here to yourself, beta has to be in radians. You don't have to change your calculator to radians because we're not doing any trig functions with it. But just for representing that angle, you have to represent it in radians. Okay, so here's an example. So let's say there's this bearing attached to the ceiling, and this looks like a pulley, but I don't mean it to be a pulley. This has to be fixed, okay? That's a terrible drawing. Okay, so this is fixed, not a pulley. And let's say that over here, the force we're trying to support is 100 newtons. And we want to figure out what force is required to support it. The coefficient of friction is 0.2. And let's first do it as shown. Second, let's do it with that cable wrapped around 3 full times. And then we're going to compare those answers to if it was a pulley. Okay. So if this was a massless, frictionless pulley, in order to keep this in static equilibrium, what would that F have to be? Yeah, 100. So what we're going to see is that you're going to have something smaller than 100 for part A, and then for part B, you're going to have something a lot smaller than that. The more times you wrap it, the more of that benefit of the belt friction you get. Okay, so what is beta? If it's not wrapped around at all, it's just leaving contact with the bearing directly on the left and directly on the right. What would beta be? Here's the meaning of it. Pi over 2. No, pi. I'm sorry. No, you're right. No, you're right. Pi. Okay, so T2 is 100. We're trying to calculate this force F, and that's equal to E to the power of 0.2 pi. And so F is equal to 100 over E to the 0.2 pi. And you get a force of 53.35 newtons. So if it's just wrapped around, you know, if the default is that being a pulley and that F would be 100 newtons, just having it thrown over the top of that bearing, if that bearing is fixed, allows that force to be almost cut in half. So now let's do it for wrapped 3 full times around. So if the contact starts here, you go 2 pi, 4 pi, 6 pi, and then another pi, so 7 pi is beta. And you have, you know, use the same equation. F is equal to 100 over E to the 0.2 times 7 pi is 1.4 pi. And you get a force of 1.23 newtons. Yep.
How like relatively big is it, like coefficient of static friction at 0.2?
Yeah, what is a coefficient of 0.2? Well, I think this stapler sliding across the table is probably more like a little higher than that, I would say, maybe 0.4. Because it has sort of rubber on the bottom. So I'd say that's 0.4. But you can always figure it out because you can, if you have a spring or something you can measure a force with, you can weigh this thing, give a little shove to it, see how much it takes to get it moving. And it's not too hard to measure coefficients of friction. Any other questions? Okay, well, that's it for belt friction. So square threaded screws. We're done with that. Belt friction, we're done with that. The only thing we have left is bearings. And that's going to take a little more time, but maybe 1 or 2 classes, and we'll be done with all that. Okay, that's it. So we will have class on Wednesday, but I know like a lot of people are going to be gone or whatever. If you can't make it, that's fine. I'll get the video up. But then remember, Thursday and Friday, there's no school. All right, see you Wednesday.